In this video, we will understand segment trees. Segment trees are range-based data structure which helps us to update and query ranges in sequences efficiently. Let's look at the following example. We have an array consisting of 4 elements 20, 30, 40 and 50. The segment tree created for this array will look like as follows. So the leaf nodes, so segment tree is does look like a binary tree where the leaf nodes will be the array elements themselves, and all the elements, all the nodes above them will be the sum of elements of its children. So 140, which is the root of the segment tree, will denote the sum of the entire array, which is 20, 30, 40, 50, and the left node of the root will denote the sum of the first half, and right node will denote the sum of the second half of the array. So now let's look at in depth what segment tree does. The simplest form of segment tree is constructed on sequences or arrays, as we saw earlier. We use segment tree to store information for some intervals, and let's say we want to update the index with some new value. So let's say we are given this array and we want to update this index with some new value. Let's say earlier it was 8 and then we want to update it to 10. Then segment tree is going to help us efficiently do that, as well as we are also going to perform queries for finding the sum in particular range. So let's say we updated 8 to 10 and then we ask what is the sum over this range. Then segment tree is going to help us solve those queries efficiently. This operation, which is the simplest form of segment trees, there are multiple advanced operations as well, but this simplest form is known as point update and range query. Let's look at a sample problem which is from CSCS. Given an array of n integers, you are asked to process q queries of the following types. First one is to update the value at position k with new value u, and the next query is to find the sum of values in particular range. And the constraints are fairly large, hence the naive approach is not possible. So this is where we are going to apply segment trees. Let's try to understand what segment tree structure looks like. Let's say we have an array of 5 integers indexed from 0 to 4. Then the segment tree looks like this, where the leaf nodes are going to denote the array values at particular index themselves. So this node, let's say the array was 1, 3, 8 and 7. Then the leaf nodes will themselves be of the same value that was present in the array, and all the nodes above them will efficiently be the sum of them, the left node and the right node. So here it will be 8 plus minus 7, hence 1. Here it will be the sum of left and right. So here it will be 1 plus 3, hence 4, and so on. The root node will consist the sum of all the array elements, which will be 1, 3, 8, 7. So here it was minus 7. And one more thing to notice here is that we will store the segment tree nodes in an array. So this structure definitely looks like a hierarchical structure, and you may think that we will require to create a tree or dynamic structure for this, but since this is a binary tree, we can store this in an array. Let's say the root node is 1 and the left node, and we subsequently number the nodes from left to right in each level. So let's say we give the numbers from left to right for level 0, which is the root node 1. Then in this level we give the numbers sequentially. Again in the third level we give the numbers 4, 5, 6 and 7, and in the last level we give 8 and 9. And one important property to notice here is that, let's say this is the node number of segment tree, let's say node ID. So let's say this was u, then you can notice that this was 2u and this was 2u plus 1, and this is satisfied for all the nodes. So if you look at 5 here, and let's say there was a new node here 10, then the node to the left of the node will be, so in this case this is different. So here would have been a new node 9 and this would have been 10 and 11. So the new node will be, let's say this was u, then this would be 2u, and the right node will be 2u plus 1. So this is the important property to represent segment tree in an array. Next up, we will look at how point updates and range queries are performed in a segment. In the last slide, we saw how the segment is constructed from the array. First of all, we initialize the leaf nodes, and we update the values for all the nodes other than leaf from bottom to top fashion. Now let's say we want to update the index at position, let's say 1 with a new value 10. Currently this is 3 and we want to update it to 10. So first of all, we must start at root, which is node 1, and we need to find out which range does this index lie. So we want to update index id equals to 1. So we know that root stores the value from 1 to 4, sorry, 0 to 4. Then the left half stores from 0 to 2 and the right half from 3 to 4. Clearly, the index 1 lies in the left half, hence we can discard this search and move ahead here, and so on until we reach the leaf node, which is this one, and update the value as this sum equals to 10. Now, since this value is updated, all the nodes from that node to the parent must be updated because their sum has now changed. So this point update operation is going to take us for finding the node that we want to update. It will going to take log n time because the height of the segment tree is log n, and hence that will be the time complexity. And also updating them will again take the same amount of time because once we reach the leaf node, we update its sum, and subsequently when we recursively reach all of the remaining node in the reverse operation, we are going to update their sums. For range query, let's say we want to find out the sum for range, let's say 0 to 3, then this operation can be performed in a similar fashion. The root node shows the value for 0 to 4 and we want to find from 0 to 3. Then we partition it into two parts at the middle point. So these are the two halves for the root node, and clearly this entire range lies within the query range. Hence this sum will be directly included, but this sum will not be included because it is partially lying. So we will again divide it into two halves, 3 3 and 4 4, and clearly this range does not lie, but this range lies completely inside the query range. Hence we will use this in the sum. Hence the answer will be 2 plus 8, which is 10. Now as you can see, in any query range L to R can be broken down into logarithmic number of nodes in the segment tree. This is true because let's say you are given very large range, let's say 1 to 1000, then there must be some node which goes from 1 to, let's say, the highest power of 2, which is less than equals to 1000. So it would have been, let's say, 512. So this answer would already have been computed, and essentially we are dividing this range each time by half. Hence the total number of nodes from which we want to find out this sum for given query range will be logarithmic, and totally in each level we will at most visit only 2 nodes. Hence the total time complexity for range queries will be log n, and for point update as well, as we saw earlier, it would be log n. Now let's look at time complexity for building. To build a segment tree, we must already have an array, and we are going to initialize a segment tree array. If you want to find out what will be the size of the segment tree array, we can find out it using this formula. The root node level will have only one node, the second will have 2, third will have 4, and so on. So the total nodes will be the sum of this 1 plus 2 plus 4 plus 8, so on, until we have the maximum height in the segment tree, and this is bounded by 4n, where n is the size of the array. Hence the segment tree array will have a size of 4n at most. To build the segment tree, we first update the values for all of the leaves, and subsequently we will update the value for their parents. The value for each node, let's say st of u, will be the sum of its left child, which is 2u, and sum of its right child, which will be 2u plus 1, and we will perform this recursively. Since there are order n leaf nodes and the height of the segment tree is order log n, so in total the building time will be order n log n. As we saw, the point update and range queries, height of the segment tree is order log n. Finding the node that we want to update will take order log n time, and updating all the nodes in this path will be done in this time only. And for similar for range queries, we found out that any query L to R can be broken down into logarithmic number of already computed steps, and this will have time complexity of order log n. Let's understand the build function for segment trees. Let's say we have an array of size n from 1 to n, index 1 to n, and segment tree denoted with variable st. As we saw, the size of the segment tree will be 4n. For 1 based indexing, we can initialize with 4n plus 1. To build the segment tree, we call this function. This first parameter is the index of the segment tree, and these are the ranges of the given array. Let's understand the base condition. Whenever we reach a leaf node, let's say this is the segment tree representation, the leaf nodes will be reached first. We will call this a build function on the root of the segment tree, but eventually we are going to reach the root first and update it before updating all the other nodes. So let's say the array was 4, 6, 10, 12. Whenever we reach a leaf node, we'll update the segment tree node with the value in the array, which is this index. So 4 will be initialized first, then 6, 10 and 12, and then this merging operation is going to happen. So this value will be updated with 4 plus 6, 10. This will be updated with 10 plus 12, 22, and the root will be initialized at the last, which is 32. This is how the build function looks like. For point update, we are using a utility function. We are passing it the index and the value, the new value that we want to update it with, and we'll call it with this. So let's say the index was 3 and the new value was 50. This will in turn call the main function inside the segment tree class. In the same way, let's say we have a segment tree which looks like this. This leaf node will store the value for index 3. Sorry, this will store for index 2 and this will store for index 3. So to find out which node that we want to update, we must know which node that we are currently at and what are the ranges for which the values are present in that node. So we started with 1 to n, the root node, which is node 1. Then we recursively check the left and right node of particular node, which is starting with root. Then we find out which either left node or right node will the updating index will lie inside. So we want to update the index either of the left subtree or the right subtree. Depending on that, we will recursively reach those nodes, and after a point we will reach the node which we want to update. And to update that, we'll simply initialize this with a new value. So for now, let's forget this exists. So this is an integer array, and we are going to update the value for this. Since we updated the leaf node, we also want to recursively change or update the values for all the ancestors of this. Since we are storing the sum of nodes inside the segment tree, we will find out the values for all the nodes that we want to update from root to the node that we have updated. So let's say index id equals to 3 needs to be updated. We have updated it to 50 by recursively reaching it from root to node, but these values also need to be updated. So once this is done, this will be updated, this will be updated, this will be updated based on this formula. For range query, it is simple. Let's say we were given I equals to 2 and j equals to 4. You need to find out the sum in this range. Then we start with the root. We know that root stores the sum from 1 to n. We want to find it for I to j. Right. So we will recursively divide it into two parts and check whether that part completely lies within our query range. If that lies completely within the query range, that means this should be included in the sum. If it lies outside the query range, then the contribution from that node must be 0. And we will find out the contribution for all the nodes by recursively dividing it into two parts, left and right. And since this condition exists, we will not traverse all the nodes in the segment. Whenever we encounter a range which lies outside the query range, we will simply terminate that subtree there by returning a 0. So with the implementation for range queries. Now this is a generic implementation for segment trees. We will use a struct for defining the nodes and implement all the necessary methods inside a class. So let's say the segment tree. For now, this problem, we were assuming that we are only storing the sum, but this implementation is going to have a simple and basic implementation for finding out the minimum, maximum, and the sum in a particular range. This is the all args constructor for node, and this is the default constructor. This is used because whenever we want to find out the value which lies outside the query range, then we need to return something default here. Right, because in case of sum, if we return 0, then sum does not affect. But in case of, let's say, minimum, we return a 0, then the answer will always be 0, because this will minimize the answer to the maximum extent. Hence, we need default values for minimum, maximum, and sum. This is the no args constructor for that. The segment tree is defined as a struct with n as the size of the array, the input array, and segment tree will have as we saw 4n plus 1 node. Since we are, for safety purpose, we are using +2 here, and we are calling the build function for root index 1 and the ranges of the array from L to R, which are 1 to n. This is the merge function which we are going to use to perform what kind of operation we want to store inside a segmented node. The build function, as we saw earlier, we will update the leaf, then we will recursively call the left and the right subtrees and perform the merge. Since to extend this further, let's say we want to find out the XOR, bitwise XOR for ranges in an array. So you can introduce a new variable here, which is XOR, and add the operation here, and it will be taken care of. Next, we have the query function, range query, and point updates. For this, we have written public functions which are easy to understand and essentially treat segment tree like a black box. So we want to find out the sum or any operation over a particular range L and R. So we will call segment tree dot query on that particular range. If you want to perform an update on a particular point with a new value, we'll simply call this function, and these functions are going to call the above private functions accordingly. And these are the implementations that we saw earlier. So for this problem, we were given n, q, and the array. We initialize the array globally and define the segment tree here globally, and we initialize the length of the array, the segment tree, which will also call the build method, which was this. After build is done, we are going to process the queries one after the other, depending on what type of query it is, and this will essentially give us the final answer. Following are the various applications of segmentary. The one we saw was the simplest one. We are simply storing the sum and we are performing point updates, but there are some advanced versions which are also going to help us to perform range updates and do the range queries. We can also find out the maximum, minimum, sum, or any bitwise operation that we saw. In this, we can extend the segmentary by storing any different parameters here and updating the merge functions accordingly. We can also perform two-dimensional queries in another version of segmentary called 2D segmentaries. There is another version called merge sort trees, which is going to store all the values in a particular range in each node of the segmentary, not necessarily just an aggregate function. Then there is persistence, which will help us to find out the value of particular range or point at a particular version of a segmentary. And there are many other advanced forms of segmentary as well, which we will go in the next video. So that's it about this video. If you found this helpful, do let me know in the comments. Thank you.